Hi, everybody. In this lecture, I'm going to discuss problem 3 of test 8 for Electrical Engineering 331. This problem was a bit involved, and so I thought that I would, even though I have made the solution to this problem available on Blackboard, I thought I would review it just to make sure that it's clear. So the problem that we're looking at here is shown right here. And by the way, this happens to be problem 2.5D in the textbook. But what we're told is that we have a linear time invariant system. And by the way, that's the kind of system that we're going to be solving in this or considering in this course. So anyway, we have a linear time invariant system, and we know that its step response is given by this function right here. And so we want to know what its response will be to this function. Okay? So the way that I think, the way that I would suggest approaching this, at least based on the knowledge that you have right now. Now, we will soon learn another technique that you might prefer. But based on what you know right now, the way that I would go about doing this problem is the following. Okay, again, we want to know the response to this input. So let's first of all get a better idea of what this input is. This x of t, if we can see that it can be written in terms of singularity functions. And we see, the first thing we see as we go from left to right, we see an r of t. So we have x of t is equal to r of t. Then we want this to flatten out, and we can make it flatten out by saying minus r of t minus 1. We want it to flatten out starting at t equals 1. But if we had just that, it would flatten out up here at a level of 1. But we want it to flatten out at a level of 0, so we have to also subtract u of t minus 1. So we have x of t, this input, is equal to r of t minus r of t minus 1 minus u of t minus 1. In other words, it's the ramp of t minus the ramp of t minus 1 minus the step of t minus 1. That is our input. So we can immediately say that the desired output, that's what we're supposed to be determining here, is the output y of t. Well, if the input is the ramp of t minus the ramp of t minus 1 minus the step of t minus 1, then the output, or the response to that x of t, is the response to the ramp of t minus the response to the ramp of t minus 1 minus the response to the step of t minus 1. So that's how we get this equation right here, that y of t is equal to y ramp of t minus y ramp of t minus 1 minus y step of t minus 1. I think that that's pretty straightforward. But the problem is that we know what y step is. That was given up here in the statement of the problem. Remember, this is y step of t. And we can express y step of t in terms of singularity functions like this. That's equal to r of t minus 2r of t minus 1 to give us this downward slope of 1 plus r of t minus 2 to make it flatten out. So this is y step of t, r of t minus 2r of t minus 1 plus r of t minus 2. So by shifting this by 1 unit, we could get this last term in y, but what about y ramp of t? Well, that's where we will use what we learned in the lesson in lecture 8, which is that y ramp of t is equal to the integral from negative infinity to t of y step of tau d tau. So we're going to have to take this y step, which is already sort of complicated, and then we're going to have to integrate it to get y ramp of t. So that's going to be even, that's going to be a bit more complicated probably. And then we're going to have to plug it in here. So that's why this problem is sort of tedious. There's nothing that's too terribly hard about it, but it's just that some of the stuff is sort of tedious. Okay. And then in the end, we're going to get this expression for y of t, and we can look at what y of t is equal to in different parts of the domain. And for this problem on the test, we're interested in f2 of t, which is how y of t behaves for t between 2 and 3. So that's what we have. And so now I'm going to go to a different page in my OneNote notebook to show you the solution of this problem. And again, this solution is available on Blackboard, but I thought that if I explained it, it would make it easier to understand. Okay, so here is the work for problem 3. And so as we just said, y step of t, which is that picture that was given, if we want to put it in terms of singularity functions, that's r of t minus 2r of t minus 1 plus r of t minus 2. And the given input, the x of t is r of t minus r of t minus 1 minus u of t minus 1. That's, you remember, we were saying that's the input is equal to the ramp of t minus the ramp of t minus 1 minus the step of t minus 1. And therefore, the response to that is the response to the ramp of t minus the response to the ramp of t minus 1 minus the response to the step of t minus 1. Now, as we said, we can find this response to the step function just by shifting what we have up here, what was given. But to find the response to the ramp function, we have to use this formula, which we learned in lecture 8, which is that the response to the ramp is equal to the integral from negative infinity to t of the response to the step. Okay? So, what happens, we want to now integrate the y step, and y step is given up here. So, what happens when we integrate that? Well, we know when we integrate delta, we get u, and when we integrate u, we get r. But what happens when we integrate r? We haven't talked about that. So let's come over here to the side and see what happens when we integrate r. And so I'm saying integral negative infinity to t of r of tau d tau. Well, as we have said before, r, the ramp function, is just tau times u of tau. So we can substitute that in for r. And the effect of that u of tau there is that, remember, u of tau is always equal to 0 if tau is less than 0. So instead of integrating from negative infinity to t, we can just integrate from 0 to t. We don't have to include the negative part of the range, because in that part of the range, u is equal to 0. And likewise, in the positive part of the range, it's equal to 1, so we don't have to write it down explicitly there either. And so we just have integral from 0 to t of tau d tau. Now, if t happens to be less than 0, I mean, I've been a little bit careless in the writing here, because this is assuming really that t is greater than 0. Because if t is less than 0, wait, let me take a break here. I think I have somebody phoning me. Okay, so I took that I took advantage of that break to be a little more careful about what I wrote here. So again, let's just start over. So we're wanting to find out what is the integral of the ramp function. We need to know that because right here, to find the response to the ramp, we have to integrate the step, but the step has a ramp function in it, so we need to know what happens when we integrate the ramp. So here's integral of r of tau d tau, which is integral, as we said, r of tau is the same thing as tau u of t, tau times u of tau. And so we can say that this integral is going to be equal to 0 if t is less than 0, because the reason we say that is that if t is less than 0, then we're only integrating over negative values of tau, and u of tau is always 0 if tau is less than 0, and so the whole integral will go away. So that's why we can say that if t is less than 0, this is simply equal to 0. On the other hand, if t is greater than 0, then we can say that this is equal to the integral from, and actually even here I need to make a change there, that lower limit can become 0. Why? Because when tau is less than 0, we don't even have to consider it, because then u is equal to 0. So this lower limit can actually be 0 to t, and then as far as u of tau itself is concerned, as long as we have the lower limit as equal to 0, that means we're only looking now at positive range of tau, and in the positive range, when tau is positive, u of tau is equal to 1, so we don't even have to explicitly write it down. So let me take one more break, and I'll change this lower limit here from negative infinity to 0, and we'll have everything precisely rigorous, which I think is important here. But when you're learning this, we want to do step by step, every little detail correct. So let's take one more quick break. Okay, so now we have that. So like I say, this lower limit can be made equal to 0, because if t is greater than 0, then the idea is we don't really have to integrate between negative infinity and 0, because that's the negative range of tau, and when tau is negative, this u of tau is just 0. So that can drop out, and we can just start at 0. So go from 0 to t. Okay, so now we're ready to go down to the next step. We still have 0 if t is less than 0. We just bring that part down. But then the integral of tau d tau becomes 1/2 tau squared from 0 to t. And so then come to the next step, and we get 0 if t is less than 0, or 1/2 t squared if t is greater than 0. So we finally get that the integral of the ramp is 1/2 t squared u of t. Okay, so now that we know that, we're ready to go ahead and evaluate what the response to the ramp is. The response to the ramp is equal to the integral of the response to the step. Okay, that's what we learned in lecture 8. But now, since this is the response to the step up here, okay, that's what we're going to have to integrate. And so when we integrate it, let's see what we get. Okay, y ramp of t is equal to, well, when we integrate r of t, we've just found out over here, we get 1/2 t squared u of t. So that's this first term. and then I bring down the minus 2. And when we integrate r of t minus 1, well, we're going to get this same thing, but with the t replaced by t minus 1. So we're going to have t minus 1 squared over 2 times u of t minus 1. Again, for when we have r of t, we get t squared over 2 u of t. When we integrate r of t minus 1, we get t minus 1 squared over 2 u of t minus 1. So it's just the same expression, but with t replaced by t minus 1. And then likewise, when we integrate the r of t minus 2, we will get the same expression, but with t replaced by t minus 2. So t minus 2 squared over 2 u of t minus 2. Okay, so all we've done here is we have, again, as this says right here, to get the response to the ramp, we have to integrate the response to the step. Here is the response to the step, and here we have integrated it using this information we obtained over here about what happens when we integrate a ramp function. So this is the integral of the r of t. Here's the integral of minus 2r of t minus 1 right here. And here is the integral of r of t minus 2. And here I've just written down almost exactly the same thing. I just made one little simplification. I multiplied the 2 times this 1/2 right here. So here is the response right here is the response of this system to a ramp of t. Here's the response of the system to the step of t. And remember, we have already said that y of t, which is what we want, is the response to the ramp of t minus the response to the ramp of t minus 1 minus the response to the step of t minus 1. So we're all ready now to finish this problem. Let's write it down then. Y of t, again, is the response to the ramp of t. And we found that right here. So notice that this is just the same as that. The first line is y sub ramp of t, just as it says right here. Then we have minus the response to the ramp of t minus 1. So this second line is the minus y ramp of t minus 1. So it's minus what we have in the first line, but with everything shifted by 1. So you see that the t becomes t minus 1 there. This t becomes t minus 1. T minus 1 now will become t minus 2. T minus 1 becomes t minus 2. T minus 2 becomes t minus 3. T minus 2 becomes t minus 3. So that's how that works. And then the final thing we have is minus y step of t minus 1. So that's going to be right here. This is minus y step of t minus 1. Now remember, this is y step up here. That's y step of t. So we want minus y step of t minus 1. So remember, r of t is t u of t. So r of t minus 1 is t minus 1 u of t minus 1. So that's where we get this one. We have minus that, and then minus a negative 2 is plus 2, and then r of t minus 1 up here would be t minus 1 u of t minus 1, but we have y step of t minus 1, so we have to shift it 1, so it becomes t minus 2 u of t minus 2. And then again, we're subtracting it here. Remember, we're subtracting. And so this becomes minus t minus, instead of t minus 2, ut minus 2. When we shift it, we get minus t minus 3, ut minus 3. So that's where those three terms come from. And now it's just a matter of bookkeeping. All we have to do for the rest of this problem really is just to make sure we don't lose track of things. And so I grouped together here all the terms multiplying u of t. Here is all the terms multiplying u of t minus 1. Here is all the terms multiplying u of t minus 2. And finally, here is all the terms multiplying u of t minus 3. And then we, do the necessary algebra in each case. And we finally come down to this expression right here. And now we're able to say what y of t, how it acts in each one of the regions of interest. Okay, when t is less than 0, this first term is multiplied by u of t. So it's equal to 0 when t is less than 0. The second term is multiplied by u of t minus 1. So it's equal to 0 when t is less than 1. The third term is equal to 0 when t is less than 2. And the fourth term is equal to 0 when t is less than 3. So everything here is equal to 0 when t is less than 0. So the first line we can just say that y of t is equal to 0 when t is less than 0. Now when t is between 0 and 1, the first term turns on because now t is greater than 0, but it's still less than 1. So all the other terms go off, or they remain off. And so when t is between 0 and 1, we just have this 1/2 t squared. Now, as we continue to increase t, get it bigger and bigger, when t gets between 1 and 2, now both of these first two terms will contribute. Because if t is greater than 1, this is certainly on, and now this one is on as well. But since t is still less than 2, the last two terms will not have turned on yet. So we just have to include these terms. So we get a t squared over 2 minus 3/2 t squared. That's how we get the minus t squared here. And then we also have plus 2t minus 1/2. That's the expression when t is between 1 and 2. Now we continue to increase t until it's greater than 2. And so then all three of these first three terms will come on. Now the last one will not be turned on yet, but all of the first three will be there. So we have a t squared over 2 and minus 3/2 t squared. So that's minus t squared. And then we have a 3/2 t squared. So that gives us, let's see here. I've lost track here. Let's see, what should I say? Okay, let me try that again. I have a t squared over 2, a minus 3/2 t squared, and a plus 3/2 t squared. So the 3/2 t squared and minus 3/2 t squared go away, so I'm just left with t squared over 2. Right there, 1/2 t squared, or t squared over 2. And then I get a 2t here, and minus 4t here, so I have minus 2t, as you can see right here. And then finally I have minus 1/2 plus 2, so plus 3/2. So that's the expression for when t is between 2 and 3. And then finally, once t gets past 3, all four terms here contribute. And if you add up all of these, you get t squared over 2 minus 3/2 t squared plus 3/2 t squared minus t squared over 2. So all the t squared terms go away. And then for t terms, you get plus 2t minus 4t plus 2t. So the t's go away. And for the constant terms, you have minus 1/2 plus 2 minus 3/2. So all the constant terms go away too. So if t is greater than 3, everything up here cancels out and you just get 0. And now for the test problem said you wanted to know what the function did for t between 2 and 3, and there's the answer, 1/2 t squared minus 2t plus 3/2. So this was an involved problem. If you followed everything with this, then I think you're doing great. But if you still have a little bit of hesitation, I encourage you just look over it again. And also I'll say that at the beginning of lecture 9, we will do another problem similar to this. You remember I said this is problem 2.5D. At the beginning of lecture 9, we're going to do problem 2.5 C, I believe it is in your book. And so this will give you still more practice with this kind of idea. So that concludes this lecture on problem 3 of test 8 in Electrical Engineering 331.